All right, let's look at the assigned problems from section 3.3. So we're given a 2x2 matrix. First thing we want to do is find its eigenvalues. So the way you find the eigenvalues is from this characteristic equation. So I'm going to find the determinant of a minus lambda I, set that equal to 0, and the values of lambda are going to be the eigenvalues. So along the major diagonal, I'm going to have -1 minus lambda and 6 minus lambda. The other two entries are going to be the same. And if I take the determinant, I will get a quadratic in terms of alpha. Or sorry, alpha in terms of lambda. So minus -12 equals 0. All right, so I get lambda squared minus 6 lambda plus 1 lambda. So minus 5 lambda. Minus 6 plus 12. So plus 6 equals 0. So I believe that's factors to lambda minus 2, lambda minus 3 equals 0. So lambda equals 2 and 3. So these are my eigenvalues. That's part A. Part B asks what's the dominant eigenvalue. So the dominant eigenvalue always comes from the one whose absolute value is greater, or the one that is furthest from 0. So in this case, that's going to be lambda equals 3. All right, now find the eigenvectors that correspond to each one. So take them one at a time. So when lambda equals 2, now I'm going to construct the matrix A minus 2i. So that matrix becomes -1 minus 2, which is -3, 2, -6, and then 6 minus 2, which is 4. So remember, when you find the eigenvalues and put them back into A minus lambda I, the way we found the eigenvalues is we're trying to force A minus lambda I to be a matrix that is singular. Or in other words, it has rows that are dependent on each other. So one row is essentially a multiple of the other. So in this case, if you were to take the first row and double it, you would wind up with the second row. So because these rows are essentially multiples of each other, I can get my eigenvector by just looking at one row or the other. So what I want to do is this. Eigenvectors I want to be non-zero. So what happens when I multiply this 2x2 matrix by my generic xy vector? I'm just going to look at one row, -3x plus 2y equals 0. So this gives us a relationship between x and y. So 2y equals 3x. So eigenvectors are not unique. I can pick any vector that fits that ratio. I believe if I make x equal to 2 and y equal to 3, then that will work. So 2 times 3 equals 6. 3 times 2 equals 6. Again, you might have an eigenvector that's totally perfect, but is not equal to 2, 3, and that's fine. As long as it fits this ratio, you're going to be okay. So then lambda equals 3. Again, I'm going to reconstruct. Now I'm going to make the matrix A minus 3i. So that'll be -4, 2, -6, 3. All right. Again, I'm going to take the top row. Top row gives me -4x plus 2y equals 0, or 2y equals 4x. I can reduce one more time, y equals 2x. So I can make an eigenvector that fits that. As long as my y coordinate is double my x coordinate, I'm fine. So I'll go with 1, 2. If x is 1 and y equals 2, that fits. So my eigenvectors are these two vectors. So that's part C. Part D, what are the straight line solutions of this system. So basically x prime equals a times x. So your straight line solutions are going to be parallel to our eigenvectors and passing through the origin. So we essentially found our straight line solutions in the previous part. I'm going to rewrite them as equations of straight lines. So our first eigenvector we found was this 2, 3. We got that from this equation 2y equals 3x. I'll write that as y equals 3 over 2x. So that's one straight line solution. The other straight line solution is going to be y equals 2x. I already had that written in that form. So straight line solutions are, very strongly related to and very similar to what your eigenvectors are. All right, E, describe the nature of the equilibrium solution at 0, 0. So bold 0, the 0 vector. So both of our eigenvalues are positive. So think about what that means for, like, if I were to write the equations, the solutions to this. Actually, this is section 3.3. I haven't talked to you about how to solve these yet. So in the case where the eigenvalues are both positive, that's where we have something called, well, I mean, it's not a new term, but we have something called a source. But now we have a source in 2 dimensions. So how does a source behave in 1 dimension? Well, you have an equilibrium point, but if you're near the equilibrium point, but you deviate from it in any to any degree, you're going to trend away from the equilibrium point. So in any first order system of linear homogeneous differential equations with constant coefficients, the only equilibrium point you will ever have is the origin. So because of that, I'm going to graph my phase portrait here. X-axis, y-axis. I know that at the origin, I have equilibrium. That I can always take for granted. What kind of equilibrium do I have? I'm calling it a source, so that means everything should trend away. So let's do this first. I can graph my straight line solutions. I know what those look like. So one has a slope of 3 over 2. So let's try to at least approximate straight lines here. 1, 2, 3, 1, 2. So one of my slopes is 3 over 2. So I have straight line solutions, and while I'm drawing these straight line solutions, what else do I know? Since my eigenvalues are both positive, I'm saying I have a source. So because of that, my vectors along this straight line trend outward from the origin. So that's going to be true in both directions. But all these vectors should line up. The other straight line solution is along the line 2x. So up 2 over 1 is going to be very similar looking. So what are these slopes going to do? See, these vectors are also going to trend away. Okay. What else can I show about this phase portrait? Well, I know that no matter where I am, again, and this is owing to I have not written the word source anywhere. So source, because basically what I have is this: 0 is less than lambda 1, which is less than lambda 2. Another way to say that both my eigenvalues are positive. In these cases, my equilibrium is fully unstable. Any initial condition that deviates from the origin at any distance is going to trend away. We also talked about which one's dominant. The dominant eigenvalue was x equals 3. which means the line y equals 2x is going to have basically more of the vectors on my plot here are going to resemble 2x as opposed to 3 over 2x. Now those slopes are pretty close to each other, so it's going to be hard to show that dominance, but what I can show you roughly here is that basically we're going to have, trends like this. Where basically everything is going to be leaving the origin. Draw some in quadrant 2 as well. And if I'm asking you for sketches by hand, I mean, they can be absolutely rough. But what are the non-negotiables here? The things you should be able to find here are the straight line solutions exactly. You should be able to tell me, sink, source, or saddle, which means you should be able to tell me, like, if I showed vectors coming into the origin here, or pointing toward the origin, that would be a red flag that something was wrong, because that is, directly contradictory to me calling this a source. What else? Again, we have a dominant eigenvalue, but our slopes or our eigenvectors are so similar. It's a little bit harder to draw a vector that is obviously with a slope of 2 rather than with a slope of 3 over 2. It's a little hard to show by hand, but suffice to say that in this vector field, most of our slopes are going to be closer to 2 than they are to 3/2. All right, so I'm going to go ahead and hold off on solution curves because problem 9 specifically asks me to draw some solution curves. So we're going to come back to that. So let's go through the same process with this system. So first, eigenvalues. So let me write the matrix A minus lambda I. And what that looks like, again, along the diagonal, I'm subtracting lambda along the major diagonal. And then I want to set the determinant of this equal to 0. So minus 2 minus lambda times 5 minus lambda minus 12 equals 0. So lambda squared minus 5 lambda plus 2 lambda. So minus 3 lambda minus 10 minus 12. I don't think so. I think I got the sign wrong on this. Minus 10 plus 12, so plus 2. Okay, equals 0. What does this factor into? I get lambda minus 1, lambda minus 2 equals 0. So lambda equals 1 and 2. So eigenvalues are 1 and 2. The dominant one is going to be the one with the greater absolute value, so that'll be lambda equals 2. Eigenvectors. So now I'm going to rebuild. So I'm still working with A minus lambda I, except now I've found the values of lambda that I care about. So the first vector I'll build is A minus 1I, which is negative 2 minus 1. So negative 3, negative 6, and then 2, 4. Same reason as before. So these rows are multiples of each other. If you're ever in doubt of that, by the way, here's something you can do. So remember, the whole way we found this new matrix and the way we find our eigenvalues is we're trying to pick a value of lambda or find a value of lambda that when I write the matrix A minus lambda I get a matrix that is linearly dependent or singular or a determinant of equals 0. All those things are equivalent. So if you're having any doubt, take the determinant. In this case, the determinant is negative 3 times 4 minus 2 times negative 6. I get negative 12 minus negative 12, that's equal to 0. So yeah, when you're ever in doubt, go ahead and do that. I think that's especially valuable when you have complex eigenvalues um, for several reasons. One of which is uh, for many of us, myself included, when the matrix has nothing but real values in it, it's usually much clearer that the rows are multiples of each other, um, as opposed to when your matrix has complex values in it. That's usually that usually doesn't jump out at you. Like in this case, if I multiply row number 2 by 1.5 or 3 halves, or negative 3 halves, I get the top row. Doesn't matter which row I take, so I'll take the one with the smaller numbers. 2x plus 4y equals 0. So I get 4y equals 2x, or, nope, flipping signs. 4y equals negative 2x, so y equals negative 1/2 x. So let's pick a good eigenvector that fits that behavior. Again, you can choose whatever values you want for your eigenvector. I like to try to only fill my eigenvector up with integers. So I'll say that x equals 2 and y equals negative 1. All right, so that's 1. The other matrix I want to build is A minus 2i, which gives minus 2 minus 2. So minus 4, minus 6, 2, 3. Okay. So 2x plus 3y equals 0. So 3y equals negative 2x, or y equals negative 2/3 x. So what's a good eigenvector here? If x is 3, then y is negative 2. All right, so got my eigenvalues. I have my eigenvectors that correspond to those eigenvalues. So D, what do the straight line solutions look like? And again, those straight line solutions come directly from my eigenvectors to the point where I think I've already written them down. So one of them is going to be y equals negative 1/2 x, and the other one's going to be y equals negative 2/3 x. And then we want to look at or talk about the equilibrium solution at 0. Again, we have real positive eigenvalues, so we're looking at a source again. So in a lot of ways, the phase portrait I'm about to draw you is going to have a lot of similarities with the previous one. So first, straight line solutions, negative 1/2 x. I'm going to be a little more rough this time, but that's okay. I know these vectors are trending away along my straight line. Why? Because it's a source. So my equilibrium is the origin. That is the only equilibrium I'll ever have. And 0, 0 will always be my equilibrium. So I have straight lines along the slope y equals negative 1/2 x passing through the origin. The other one is negative 2/3 x. Again, these slopes are very similar. This one's a little steeper. And for the same reason as our other eigenvectors, or our other eigenvalue, we have the vectors pointing away because this is a source. And then again, it's going to be hard to kind of show graphically, qualitatively, that one of my eigenvectors or eigenvalues is dominant because they're so close to, so the slopes are so similar. Negative 0.5x versus negative 0.667x. But most of my slopes are going to more closely resemble which slope? I said lambda equals 2 is dominant, and that goes with the vector of negative 2/3. So again, we can kind of fill out, the rest of this phase portrait, accordingly. Basically, you're going to see this behavior away from the origin, not pretty much wherever you are, absolutely everywhere you are, with the lone exception being the origin. All right, so now for question 9, what question 9 says to do is to, I'm covering it up, aren't I? Let's move this menu. Let's actually just make it go away. All right, so question 9, solve each linear systems for the initial condition 2, 2. So how do we solve systems like this? So the good news is we have all the pieces to do that. So the way we write the solutions here, x of t and y of t, how do I populate these things now? It's going to be equal to c1, so some constant that we'll have to figure out later, times, let me give these eigenvectors names. I'll call this one u and this one v. And I'll call the eigenvalues lambda 1, lambda 2. So remember, your eigenvalues and eigenvectors they correspond to each other. I can't mix them up. So my x value or my x solution is going to incorporate, the x coordinates of both my eigenvectors and both of my eigenvalues. So c1 times u1 times e to the lambda 1t. So the x coordinate of my eigenvector times e to the eigenvalue times t. And then we're going to have a corresponding term for the other eigenvalue and eigenvector. So c2 v1 e to the lambda 2, because vector v corresponds to eigenvalue 2, t. And then what changes when we figure out the value for y? Basically, I'm going to write a very similar thing, except now I want the y component of all these vectors, or both those vectors. So c2 v2 e to the lambda 2 t. So the thing that I just wrote down has nothing to do with any particular system of equations. This is general. So now I'm going to use this to work out my solution for our system. So C1 is a constant we'll find out at the very end. U1 is 2. So I'll write this as 2C1 e to the 2t plus 1C2, because that's the coordinate of the eigenvector that I want, C2 e to the 3t. And y of t equals C1 U2, so 3C1 e to the 2t plus 2C2 e to the 3t. So this is our general solution. The only way we can get the constants is if we know the initial condition, which we do. So what's x of 0? X of 0 is equal to 2C1 plus C2, which equals 2. Y of 0 is equal to 3C1 plus 2C2, and that's equal to 2 as well. All right, so what's a good way to solve this system? I'm going to double the first equation, so I'm running out of space here, but that's okay. If I double that first equation, I get 4c1 plus 2c2 equals 4, and 3c1 plus 2c2 equals 2. If I subtract straight down, what do I get? I get c1 equals 2. If c1 equals 2, I can plug it back into either one of my equations, and I get 2 times 2, 4 plus c2 equals 2, so c2 equals negative 2. All right, so what's my solution here? 2 times c1, which is 4, c2 minus 2, 3c1, so 6, and 2c2, so minus 4. So this right here is my solution. The last thing I want to do here is let's actually plot a curve that mimics 2, 2. So I've already tried to draw in the vector field, so I can kind of follow this out a little bit and follow it backwards. So even though this is a source, it looks like I do have some behavior that trends toward the origin for a bit, but eventually we're going to see some behavior like this. So that's a rough sketch of what that solution will look like with that initial value. All right, so let's solve this one as well. So we can write out the general solution in much the same way. So x of t will equal to c1 times 2, so 2c1, e to the, what was the eigenvalue for the first one? E to the 1t, plus 3c2 times e to the 2t, because the other lambda value was 2. And then y of t is equal to negative c1 e to the t minus 2c2 e to the 2t. Okay, now we have the same initial value, so let's go ahead and find our constants. X of 0 equals 2c1 plus 3c2 equals 2. Y of 0 equals negative c1 minus 2c2, and that equals 2 as well. I'm going to go ahead and double the bottom equation this time. So 2c1 plus 3c2 equals 2. Negative 2c1 minus 4c2 equals 4. Adding straight down gives me negative c2 equals 6. So c2 equals 6. Let me write this up above because I feel like I'm encroaching on my phase plot. So negative c2 equals negative 6, which means that looks like c1 equals negative 10. Make sure of that. So c2 equals negative 6. So negative 2 times negative 6 is 12. Negative c1 equals negative 10. So c1 equals positive 10. c1 equals 10. And I'll check the other equation to make sure that fits too. 2 times 10 is 20. Plus 3 times negative 6 is negative 18. 20 minus 18 is 2. All right, good. So now let's fix our solution here. 20 e to the t plus 3c2, so minus 18 e to the 2t minus 10 e to the t plus 12 e to the 2t. And our initial solution here is going to, I think it's going to look similar in behavior to the one I just drew. But I think we're See what the last one looked like. So the vectors it was following was different, but still, we're going to see this behavior that doesn't really overall trend any closer to the origin. All right, that is all for section 3.3.